Okay, ladies and gents, so today we're just going to check through the homework from the last day. So it asked you to calculate the molar masses, and here they all are in the middle column, and then it asked you to put them in order of increasing weaker van der Waals forces. So the lowest number here, 2, will have the least amount of van der Waals forces, going all the way up to CCl4, which has a molar mass of 154, and that will have the most. So this will have the least van der Waals, and this will have the most. So I hope you were good at your maths with all of your mass numbers. The next question then wanted you to determine which non-polar molecule has the highest boiling point and which has the lowest boiling point. So because these guys are all the same element, straight away these are all non-polar. Here this is non-polar because it by rule 1 it is a symmetrical molecule, CH4. It has non-polar bonds, so that will definitely make it a non-polar molecule. CCl4, while it has polar bonds, the dipole moments cancel, so this is also non-polar. Similarly for CO2, the dipole moments cancel, so there is electronegativity difference when you draw it. It will have the delta positive, delta negatives here, but because it's a symmetrical molecule, by rule 1 they will cancel. The last two are the two polar, and you don't even need to calculate electronegativity values. It's the fact that they have these lone pairs here. This makes these polar bonds when you do the maths, but the fact that the lone pairs here makes these polar molecules. So I've taken the order from the previous table, and out of all of these, because hydrogen has the least amount of van der Waals, it will have the lowest boiling point, and because CCl4 had the highest van der Waals, it will have the highest boiling point. The last thing I asked you to do then was see, could you state and explain the relationship? So you're looking, the state is always what's going to happen to the y-axis as you move along the x. So here, as your number of electrons increases, the boiling point of your molecule increases. So that is the state. So please make sure you have that in your notes. And the explain part then is the x-axis. So as the molar mass increases, you have more of the weaker van der Waals, and you will have higher boiling points. So the bigger the molecule, the more electrons, the more van der Waals is present. So today we're going to look at the other intermolecular forces that are present. Oh, apologies, we had just two little questions. So in 2004 it asked you for the intermolecular force in N2 and Y. So N2 is non-polar molecule. It's only going to have weaker van der Waals, and the reason why it only has weaker van der Waals is because it's a non-polar molecule. You'll see today that we'll be looking at things that have intermolecular forces other than van der Waals will be polar. And then in 2017 it asked you for the intermolecular forces in ammonia, and you should be able to have gotten one of them, which is the weakest van der Waals. We haven't done this yet, but if you want to make a note of it now, we will come back to it today. So ammonia has 2 intermolecular forces. It'll have the weakest van der Waals, and after today you'll be able to figure out what is the second IMF that ammonia has. Okay, so we're still looking at our hints for intermolecular forces, and we have said that everything has van der Waals. So that's easy. You know, every time they ask you what intermolecular force is present, it's got to be the weaker van der Waals, and then it could be just van der Waals, or it could be one or two others. So in my book now, we're on page 166. You may not have all of this kind of laid out in the way I do, but I'm trying to give you little extra hints and tips to see can you help figure it out. So we have the next intermolecular force is called dipole-dipole interactions, and this gets the descriptor stronger because it's stronger than van der Waals. So how do we figure out if these intermolecular forces are present? So the first thing that we do is we take the electronegativity values and we work out and if the number is between 0.4 and 0.7, there's a good strong possibility that it is going to have stronger dipole-dipole interactions. The second thing we do is we have to have a look at the molecule, and does rule 2 or rule 3 apply in our rules? So is there something, one element different around a central molecule, as you might see in CH3Cl, so this is a rule 2, or is there a lone pair present? So we'll just use water as our example. Is there a lone pair present? So if you were to do the maths on this, this would be our minus, this would be our positive here, and here we'd have a minus and a partial positive, and here we'd have a partial positive and a minus. So straight away both of these compounds hit this first bullet point, and are these polar molecules? This one is by rule 2 because I have one thing different around the outside, and this is by rule 3 because there's lone pairs present. So this will be really strongly polar because not only does it have lone pairs, it has the dipoles as well. So when we talk about stronger dipole-dipole interaction, we're looking for the presence of a dipole in one molecule, and then when it cozies up to its exact image, then you will get the dipole-dipole interactions. So I'd like you just to pause very quickly for yourself and use the table at the back of the book and work out the electronegativity values for these guys here. And tell me, polar or non-polar? Is there a dipole? So polar or non-polar, and do these have a dipole? Okay, so for HH, when you do the maths, it's the electronegativity difference is going to be equal to 0. That makes it what is called non-polar covalent because it fits in the range between 0.4 and less than or equal to, between 0 and less than or equal to 0.4. So that makes it non-polar covalent. When you do the maths here, it comes out to be in the range of the greater than 0.4 to 1.7. So this makes this a polar molecule because there's nothing to change it, and we put our little delta positive and delta negative over these guys. So this molecule has a permanent dipole. This guy here, similarly, when we do our electronegativity numbers, it's going to hit the 0.4 to 1.7. It is a polar molecule, and for that reason we have to put these guys in it. So again, this has a permanent dipole present. So when we talk about our van der Waals, this guy over here, the hydrogen, is going to just have weaker van der Waals. These guys are obviously both going to have weaker van der Waals, and we're going to now figure out by the end of today which of the other intermolecular forces do these have. So they each have one other intermolecular force. Okay, but I just highlight the fact that these guys both have permanent dipoles present, and that the permanent dipoles is the fact that we're putting this little thing on our diagram and there's nothing to cancel them out. So to explain what dipole-dipole interactions are, polar molecules will have these permanent dipoles, and the molecules will align themselves positive to negative, positive to negative, positive to negative. We saw this diagram earlier. This is just showing you the distribution of the electrons. So if this is HCl, most of my electrons are with the chlorine. Okay, so what happens is that this negative terminal here is going to be attracted to this positive terminal. This negative, little delta negative, is going to be attracted to this delta positive, and that just continues on for the whole solution or gas or whatever it is of our solid hydrogen chloride. So they're all going to be attracted to each other. Okay, so this is showing you a dipole-dipole interaction. This is the dipole-dipole interaction. So it's the delta positive of one with the delta negative of another. So this is showing you your dipole-dipole interaction. So it is the delta negative of one HCl plus the delta positive of a different HCl. That is your dipole-dipole interaction. So we're going to have just a little look here. So if we were to calculate the molar mass, both of these have very similar molar masses, but the methanol has a much, much higher boiling point. Now, we haven't done Kelvin yet, but it's another measure of temperature that chemists use all of the time. But you can see from these numbers that 252 is bigger than 169. And to explain why, so they give you the words usually, and you have to work out the formula, and you have to then explain why the methanol has a bigger boiling point than ethene. And to do that, you've got to figure out which intermolecular forces are present. So we know from looking at them, similar molecular weight must mean they have similar van der Waals. So the question is now, do they have this dipole-dipole interaction? So similar van der Waals for this one and this one, because they are the same molecular mass. Okay, so when we look at ethene, and if we were to take our electronegativity value and we take away C minus H, we will get a value that comes between the 0 less than or equal to 0.4. So the CH bond is nonpolar. By rule 1, I have the same things around the outside. So it's a nonpolar bond, and it's also a nonpolar molecule. So because of that, the only intermolecular force that's going to be there is the weaker van der Waals. So ethene has only weaker van der Waals to overcome. So that's the only intermolecular force it has, and that's why its boiling point is the 169 Kelvin. The methanol, on the other hand, when you do your piece of maths, for the C and the H, we've done as above, so it's a non-polar bond. But when we do the maths for the C and the O, we will find that the value will be between greater than 0.4 and 1.7. So it is a polar bond. And by rule 2, there's nothing to cancel these guys out. So this is a polar molecule. So we've said everything has van der Waals, so the methanol not only has weaker van der Waals, but it also now has this stronger dipole-dipole interactions to overcome. So that's why this then has its boiling point of 252 Kelvin, because it not only has the weaker van der Waals to overcome, but now it's got this stronger dipole-dipole action to overcome. So I hope now that makes sense to you. So the last intermolecular force we're going to look at is what's called hydrogen bonding. And this gets the strongest descriptor because of all of the intermolecular forces. This is the one that you've got to input way more energy to actually disrupt it. So that means these guys will have, if you have hydrogen bonding, it will, you have to overcome it. So therefore your boiling points and melting points will have to be very high. So this is the third and the final intermolecular force, and not all molecules will have it. So how do we figure out if something has strongest hydrogen bonding? Well, this is the hint that we use. I call it NOF. And essentially what we're looking for is a NH bond, an FH bond, or an OH bond somewhere in our compound. And once we have that present, there is hydrogen bonding. So the hint is NOF. So in terms of your blurb, well, hydrogen bonding, it's kind of supercharged dipole-dipole interactions. So earlier we did HCl and we did HF, and they both ended up having the little delta positives, delta negatives. This is the one that has the dipole-dipole, but because this has this HF bond, this puts this into the hydrogen bond category. So it's supercharged hydrogen bonding, and you only get it with NH, FH, and OH. And the reason why it's so supercharged is the hydrogen is bound to something that's very small and very electronegative. So it's pulling electrons to it all of the time. So the 3 bonds are the NH, the OH, and the FH. And they all have a strong permanent dipole. So we'll be able to write the little delta positives and delta negatives on one side of it. That's your dipole. And it will have a hydrogen atom in there. And the thing that it's bound to has at least one lone pair of electrons. So those things combined together will make for hydrogen bonding. Now, these were the things we did earlier, so I'm just going to go through them again. So we have HH, it's got to be nonpolar covalent because there's no difference in electronegativity. It only has weaker van der Waals. HCl, when we went through it, has a permanent dipole. And it will have weaker van der Waals and it will have the strong dipole-dipole as its intermolecular forces. And for the HF now, we worked out last time that this also has a permanent dipole, but it's special because of the NOF, and this is the FH version of NOF. So for that reason, HF has weaker van der Waals and strongest hydrogen bonding. So if you were looking at boiling points would be increasing as we go from left to right because of the intermolecular forces that are involved. Okay, so once you have strongest hydrogen bonding, you're going to have a really, really, really high boiling point. Now this is the HF, and you should have this in your book. So when you do your piece of maths, we've said the H will be delta positive, the fluorine will be delta negative, and we have these 3 lone pairs. So fluorine atoms have 3 electron lone pairs that they can bond with other HF molecules. So it's not, so realistically, this little guy down here has a slight delta negative, this has a delta negative, this has a delta negative, and they are now going to be attracted, you'll see it in the next diagram, to other HF molecules. So this is just showing you a whole load of HFs. So these are showing you the delta positive portions of your molecule. This kind of dashed line here, this is your hydrogen bond, your interaction between them. And the note down here says, well, we've already talked about that hydrogen bond is the strongest intermolecular force, but each lone pair in F can form hydrogen bonds. So there's also another hydrogen bond coming down here. There'd be another one going that way, this way, this way. So you can see now, because there are all of these bonding attachments, you have to disrupt each one of those to melt it from a solid to a liquid or boil it from a liquid to a gas. So the more lone pairs you have, the higher your hydrogen bonding will be, and therefore the higher your melting point will be. Okay, and there's putting in the delta negatives are being put in too. Now you have to be able to draw hydrogen bonding in both anything that's in group 4, let me just turn around, in group 5 and in group 6. So the things that you have to do are, you have to, so if we start with water, you draw in your lone pairs of water like so. You have to draw in the polarity, so you show the delta negatives and you show the delta positives. And you're going to use a dashed line to show the hydrogen bond, and this part here, the straight line nature of the hydrogen bond. What that means is the hydrogen bond will bond with the lone pair that's kind of in a line with it, and this whole thing is now in a straight line. So I'm just going to change the color pen if it will let me. So this is really, really important, that this whole thing is in a straight line. So that's what that little last point means. So if I was filling in this here, I'd still have my H's. I still need to put in my delta positive, delta negative, delta negative, delta positive. And that is showing you now the hydrogen bond. So this little dashed line here is the actual hydrogen bond. There obviously there'd be another one if you so wished to come up here, dashed line. It is going to be going for a hydrogen and the lone pair. So I still have another straight line. And I'll fill it in a different color in a second, but this would be my second. So everything in here is going in a straight line as possible. Okay, and that is the hydrogen bond. So you have to show your dipoles, you have to show your lone pairs, you use a dashed line for your hydrogen bond, and you show the hydrogen bond as being a straight line from the lone pair of one all the way through to the hydrogen, to the lone pair of the next, all the way through to the hydrogen. Okay, so pause that if you need to. Now, water is exceptionally weird in terms of its melting point and boiling point. It doesn't behave as it should. So this is kind of long, but it goes through a lot of stuff.
Water. You might not see it, but this is probably the strangest thing in the universe. Here's why. Every molecule of water on the Earth, and inside you or any other living thing, has existed for billions of years. After it came to Earth, that water has been cycling through rocks, air, animals, plants, and back again. Each molecule has been on an incredible voyage before coming to you. At some point, the water inside you would have been inside dinosaurs, bacteria, the oceans, storm clouds, the polar ice caps, and much more. All of the water on Earth is alien. They might be a familiar part of our world, but our oceans formed hundreds of millions of years after our planet took shape. The water arrived on asteroids and comets from space, objects from the edge of our solar system. They were leftovers of the vast clouds of dust and rocks that didn't quite make it into planets. This is the origin of all the water you can see on the Earth. Water doesn't follow the normal rules of chemistry. For a start, it shouldn't really be a liquid on our planet. A water molecule is made from two very light atoms, hydrogen and oxygen. And at the temperatures and pressures on the surface of the Earth, rules of chemistry say that water should be a gas. And unlike any other chemical, when water freezes, it expands. And so ice floats on water. Now, you see this every day, but take a moment to think about how weird that is. Over time, this odd behaviour has been very useful. By insulating the water underneath, floating ice has enabled complex life to survive and evolve on our planet, despite the many ice ages that have frozen the Earth's surface solid. And the strangeness just goes on and on. Did you know that hot water freezes faster than cold? Yes, really. No one knows why. Water molecules can flow upwards against the force of gravity. That's because they love to stick to each other. They're so good at it that they can actually pull each other up through tiny channels, such as the tiny blood vessels in your body. That's how oxygen and nutrients reach the edges of your brain. The same process, called capillary action, allows plants to move water from deep below the ground to nourish the leaves and branches that grow in the sunshine. Our solar system is drowning in water. Once upon a time, we thought that we were alone on Earth with so much water. But in fact, it's the second most common molecule in the universe. We now know there's water on the Moon, on Mars, Pluto. In fact, there's H2O from almost every object in our solar system. And where there's water, there could be life. So pour yourself a glass of water now and take a good look at this colourless, featureless and tasteless material. It's actually remarkable. It breaks so many rules of chemistry that scientists struggle to understand it. But without its rebel behaviour, none of us, nor our world, would exist. You're only here watching this video because water is so strange.
Water is the liquid of life. We drink it, we bathe in it, we farm, cook, and clean with it. It's the most abundant molecule in our bodies, in fact, every life form we know of, would die without it. But most importantly, without water, we wouldn't have iced tea. Iced tea. Why do these ice cubes float? If these were cubes of solid argon in a cup of liquid argon, they would sink, and the same goes for most other substances. But solid water, aka ice, is somehow less dense than liquid water. How's that possible? You already know that every water molecule is made up of 2 hydrogen atoms bonded to 1 oxygen atom. Let's look at a few of the molecules in a drop of water, and let's say the temperature is 25 degrees Celsius. The molecules are bending, stretching, spinning, and moving through space. Now, let's lower the temperature, which will reduce the amount of kinetic energy each of these molecules has. So they'll bend, stretch, spin, and move less. And that means that on average, they'll take up less space. Now you'd think that as the liquid water starts to freeze, the molecules would just pack together more and more closely. But that's not what happens. Water has a special kind of interaction between molecules that most other substances don't have, and it's called a hydrogen bond. Now remember that in a covalent bond, 2 electrons are shared, usually unequally, between atoms. In a hydrogen bond, a hydrogen atom is shared, also unequally, between atoms. 1 hydrogen bond looks like this. 2 look like this. Here's 3, and 4, and 5, 6, 7, 8, 9, 10, 11, 12. I could go on. In a single drop of water, hydrogen bonds form extended networks between hundreds, thousands, millions, billions, trillions of molecules, and these bonds are constantly breaking and reforming. Now back to our water as it cools down. Above 4 degrees Celsius, the kinetic energy of the water molecules keeps their interactions with each other short. Hydrogen bonds form and break like high school relationships, that is to say, quickly. But below 4 degrees, the kinetic energy of the water molecules starts to fall below the energy of the hydrogen bonds. So hydrogen bonds form much more frequently than they break, and beautiful structures start to emerge from the chaos. This is what solid water, ice, looks like on the molecular level. Notice that the ordered hexagonal structure is less dense than the disordered structure of liquid water. And you know that if an object is less dense than the fluid it's in, it will float. So, ice floats on water. So what? Well, let's consider a world without floating ice. The coldest part of the ocean would be the pitch-black ocean floor, once frozen, always frozen. Forget lobster rolls, since crustaceans would lose their habitats, or sushi, since kelp forests wouldn't grow. What would Canadian kids do in winter without pond hockey or ice fishing? And forget James Cameron's Oscar, because the Titanic totally would have made it. Say goodbye to the white polar ice caps reflecting sunlight that would otherwise bake the planet. In fact, forget the oceans as we know them, which at over 70% of the Earth's surface area regulate the atmosphere of the whole planet. But worst of all, there would be no iced tea. Iced tea.
Alrighty, so there's a huge amount of stuff in that, but it's an introduction. We'll finish about the density, but hydrogen bonds are always present between water molecules, and once you cool water, the hydrogen bonds stay fixed, and that's why ice floats, and that's also why your pipes burst, because instead of the water molecules condensing and packing in tightly, they actually take up more space. Now, you have this graph and you're going to do some things with it for homework for me, and I'm going to help you out. Before we do that, we're going to kind of write an intermolecular force decision tree, for want of a better way to explain it. So we've said everything has weaker van der Waals, so that's always going to be the top of your tree. And if it's a non-polar molecule, then it has nothing else. So all it has is going to have van der Waals. But if it is a polar molecule and there's no NOF, so you just have your dipole present but no NOF, then it's also going to have stronger dipole-dipole interactions. And our last bit of our decision tree is that if you have a polar molecule but there is NOF present, so that means NH, OH or FH, then you are going to have weaker van der Waals and strongest hydrogen bonding. So if you want to use this little decision tree to help you figure some stuff out, please absolutely do. So for homework, you're going to be looking at this graph, and you are going to find out the intermolecular forces that each compound has in this graph. So you're either learning to do it, or you're recognizing what the shape is and the electronegativity difference between your bonds. You're going to use your rules, and obviously the easiest thing is NOF present, because that's going to give you straight away hydrogen bonding, so that makes it easy. So you're going to work out the intermolecular force in each compound, and I'm going to help you because they come in groups. So CH4, SiH4, GeH4 and SnH4 will have the same intermolecular force. So you can do the maths, but they will all have the same intermolecular force. So if you find out one, you find out the rest. H2O is standalone. It's the only one there that is weird. And then we have H2S, H2SE, and H2TE, and they are the third group. Okay, so they each will be one of the rules when we were working out polar molecules. So give it your best shot. These are the questions. So the first thing you're going to do is you determine your intermolecular forces for all of your compounds. You're going to state and explain the trends in group 4 hydrides, so that's the CH4 line, and you're going to state and explain the trends in group 6 hydrides, and that's the H2O. So remember, we said the state and explain is what happens, the state is what happens to Y as you go along X, and the explain is now using what you know about the IMFs that each molecule has. So give it a go. We are pretty much now at the end of covalent bonding. We've only a little short bit to do, so you are doing great.